Hello, this is Jesse, and in tutorial 5 today, I'm going to be using Mimi, MAST, and TomTom. This tutorial will be using this Mimi suite, and we will be using Mimi for motif discovery, MAST to search for sequences that contain our motif, and TomTom to search with our motif against a database of known motifs. We're going to start off by just getting a sequence to work with. So here I went to Uniprot KB. In the search bar, I typed in Defensin, searched, and the first result is what we're going to be using today. Go to Format, FastA, copy and paste this sequence, open up a BLAST-P suite, and put your sequence into the query box, the one that we just copied and pasted from Uniprot. And then I'm going to go ahead and click BLAST-P just to get things going a little bit quicker. And then I'm going to go ahead and click BLAST. So now this is going to perform a BLAST-P search. We're going to be gathering up sequences that we're going to use in the Mimi suite to construct a de novo motif. So this is what we're going to use later. So here, I'm also going to demonstrate one of the features of the new blast page results. So here, notice the top filter results. We can filter our results from percent identity to e-value. We can keep the here's our significant alignments, and we can filter them. So first, I'm going to filter them. Just say in this case, I'm interested in ones that are between 60% identity and 80% identity. Or let's say 100 for this case. 60 to 100. Filter. And then here we have our results. 100% to all the way between 60. So between 60 to 100. And we can filter it further. So we want 60 to 70, and we should get less. Here it is. And maybe we're only interested in these. So we can actually take these and submit it to our BLAST result, or submit these to the Mimi suite. So we can open up the suite. So here is the URL. I'm going to open this up in Chrome. I'm going to go to Motif Discovery, click on Mimi. So Mimi discovers novel ungapped motifs and your sequences. Mimi splits variable length patterns into 2 or more separate motifs. So we're going to be creating a motif with these BLAST results. Mimi will perform that for you, do the calculations for you, and bring back motifs that are ungapped. If they do have a motif that appears to be gapped, then they're going to split that and make 2 motifs. Okay, so first let's take our results. So here, what we'll do is we'll go to download. We'll go to FastA complete sequence. Here's our sequence right here. I'm going to just put this over here, and we'll rename this sample 5, and I'll put it .fasta. Okay, so here we have our sequences that we just easily filtered based off of percent identity. Next, go to Mimi, and then in my tutorial that I already have set up here, you just need to upload your sequences. So in this case, DNA, RNA, or protein, we need to actually choose the file that we want to, or my bad, in this case we want to input the primary sequences, enter sequences in which you want to find the motif. So here we can go to desktop, and I'm going to go to example 5.fasta, which is the sequences that I just got from this BLAST search. Next, how many motifs should Mimi find? Just going to put 3 in this example. You can go more or less. Now, one thing I should not forget to tell y'all is that if you get any homework question that's using Mimi, please try to submit the job as soon as possible. Sometimes it can take days to get the results back. So I'm telling you now to upload the job as soon as you can. So you won't be emailing me telling me that it's taking too long. If you do it in the appropriate time, you should be able to get this done before the deadline. So we're going to go to select the mode of discovery mode, classic, make sure everything's correct. How do you expect the motive size to be distributed in sequences? We'll just say 0 or 1 occurrence per sequence. Keep everything normal, or keep everything default. And then we're going to submit. Okay, here I put 5, but I'm only going to put 3 in this case. So we're going to start search. And then we have a set of 23 protein sequences between 5 and 100 in length. And we're going to wait for the job to be done. You can leave and you can come back to this site later. Your jobs will be sent right here. Here it is. Right, and you can always come back to it. It's going to memorize and keep your job submission. And you come back to it later. And we will once we get the results back, we can see what motif we have. Okay, so once we get our results from the job we submitted for Mimi to generate a motif or discover them, we're going to click on Mimi HTML output, and then we get our discovered motifs that they were able to pick out from the group of sequences that we submitted. So here we have our 3 of the motifs, and notice how previously that we asked to only find 3, and so they stopped at 3, right? So here's 3. You could ask for 5, and they'll try to find 5. So here each motif has a location, right? It has the p-value, how reliable the value is, and then it has the e-value. So what's the chance of us getting this particular sequence? So here we can go to submit and or download, and we can click on MAST. Click on submit for MAST search. MAST, you click over here where it says motif scanning. MAST searches sequences for matches to a set of motifs and sorts the sequences by best combined match to all motifs. So in this case, we're going to submit the first motif discovered for a MAST search. MAST is going to be the output's going to be finding any sequences that have our motif, and then the best match will be at the top. So you just submit the job. So in this case, we're going to just use the ab initio predicted proteins and then the Hungarian mouse. And then database version 96. We can click on, and then click start search. And then for me, I've already had this job already done. So click on MAST and we go to MAST HTML output. From there, it gives us the top match. Here it is. When we click here, it shows us where it matched. Motif 1, and here's where it matched in the sequence, in the protein. Okay, so this is what the MAST can do. It's going to search against the database. In this case, the database is the mouse. And then the predicted proteins that the mouse has, we will be searching with our motif against the proteins of that mouse. And it will bring back the top result and tell us where that protein lines, where the motif lines up with the given sequence found in the mouse. So that's all we're doing. We're just trying to see, given a protein database, in this case the mouse database, does our motif occur? Do we have any similarity, right? And these are other sequences too. So we can click on this one if you want. Here's the position. This is the sequence of the mouse protein right here, the line. And then here is where our motif matched up with the sequence right here. So position 330 and ends at 379. We can look at other ones too. So here we have motif matching in two different cases, right? Two different cases on the same protein that this mouse has. And it gives you the start position and the end, and then start and end. So I hope that is clear. Next, we can go to TomTom. TomTom is going to be comparing our motif against a database of known motifs. So we click on TomTom, we're going to need to submit a motif here. To get our motif, we can go to the previous Mimi results that we had. Go to Mimi HTML output. So there's the same sequence. You can do others if you want, depending on the homework question. But in this case, just for an example, I'm going to use the first one. Here's the MAST, or my bad, download motif. Format, we don't want the matrix, we want the FASTA format. And then you can submit all of these sequences that make this consensus pattern right here. But I'm just going to take just the first one, just as an example to show you what it's going to be doing. So you take it here, copy and paste it. You can download the whole thing if you want. But in this example, I'm just going to use the first sequence. In the homework, you might be asked to use the entire group that is the result of this, that makes the result right here at the top, the consensus pattern. But I'm only taking the top right now. So go back. We can go to TomTom, and then you just paste your sequence in. You can go to protein, and then we can go down, protein motifs, and then you submit your job, start search. Everything else is going to be the same. I've been searching against eukaryotes because remember that when we got the sequence, the defensin, it's from the human, so, and all the other sequences gathered up were eukaryotes. So I'm going to be searching against eukaryotes. You can also go against bacteria too, but in this example, I'm just going to be searching against other eukaryotic organisms that might have this motif or a similar motif. Because right now TomTom is searching against a database of known motifs, so there might be already a motif that is similar to the motif that Mimi was able to construct. So you just click Start Search. I already have this job done for us. So TomTom HTML output, and then here's the best motif match. So we got matches. We got 12, and then we can look at each individual one. Here's the list. There should be 12 of them. Here's the first one. So it gives us the statistics, right? P-value, E-value, and then Q-value. And you can always click on these, and then if you forget what they mean, this website's useful, provides additional information about what they are. Close. And then you have the results of each 12 matches. You can scroll through these. You might be asked questions in your homework about this. But here you're able to look at the matches. Right, so this will be whatever the sequence is, right? If you have your sequence right here, the first one we submitted has some similarity, right? May not be significant. Look at the E-value. Chances are high that this match has occurred by chance. But we look further up from the top. Might be a little bit more significant result here, but not really. So in some cases, you might need to start back and redo your search, or maybe you might take it. It's a high E-value, but there might be some meaning. You might be able to determine if there is any significance with the consensus pattern that you used and any already known motifs. Okay, so that's MAST and TomTom. Okay, so for the next half of this tutorial, we're going to use MimiSuite to find a potential motif in the adenylation domain of a non-ribosomal peptide synthase and use that motif to search for amino acid adenylation domain in a given species. So first, we're going to start off with gramicidin S synthase 1. So here I already have UniProt open, and I already have this session number for you, just to make things a little bit quicker and easy for you as you practice going through this stuff. Okay, so first we start off with the protein, and then next what we're going to need to do is we're going to use Interpro to find the positions of the domain of interest. So we can go to None, we can go to Family and Domains, then we're going to use Interpro. We can click on View Protein and Interpro. And then here we have annotations and the positions of our sequence. We have domains and repeats. You can see here that we already have amino acid adenylation domain here. So this protein does have the domain that we're interested in. It has other domains, but we're interested in the adenylation domain. In this case, the adenylation domain is right here, amino acid adenylation domain. You can click on the accession number if you want to read further into the function of the adenylation domain. But we're interested in just obtaining the sequence itself. So here is the position. Amino acid adenylation domain, position 66 and 460. So I have that right here. Okay, we want to use this to create a motif, but we need other sequences that also have this amino acid adenylation domain. So what we need to do is we need to get the sequence and get position 66 and 460 and take out only that sequence. So we can click down here, maybe see if UniProt has it annotated here, but it looks like it does not. Family domains, so only Interpro has it annotated for us. You might find in other non-ribosomal peptide synthases, it might have the condensation domain or the amino acid adenylation domain already right here for you, and you click on it, and it'll give you the positions that you want, position 66 and 460. In this case, we don't have that, so we have to manually get the sequence, this position, we've got to get the sequences between the residues between 66 and 460. So what we can do is go to FASTA format, and we can copy and paste this sequence into JalView. Once we get JalView up and running, I can take the sequence we want and we can get position 66 and 460. Okay, so we can go to File, Input Alignment from Text Box. I'm just going to paste the sequence here. Okay, I'm going to click New Window. Here's our sequence. So we want 66. Let me make sure I'm getting what I want. 66, 460. So here's 60, here's 65, and then here's 66. And then we're just going to go all the way down to 460. Once we get to 460, we're going to output this subsection of the sequence into a text box. So I'm going to right click, selection, output the text box in FASTA format. Here it is, 66 to 460. And it even gives us in FASTA format exactly what we need. So here's what we have. This is what we're interested in right now. We want to use this sequence to gather similar sequences that are, so we're basically looking for other sequences that have some similarity to this adenylation domain. So we need to go here, and then we can do a blast search. So let's continue on in this tutorial. I just went through all this, now we can use blast. Okay, now in this example, I just use smart blast to go ahead and select sequences that are similar for me and to pick the best sequences from, or what they might deem as good, interesting sequences that are from different organisms, different databases, and so forth. Okay, so we're going to go here, click Smart Blast. We're going to input our sequence here. Take the sequence, copy, and paste. Blast. And then once we get our results, we can notice how we have our sequence right here, exactly what we want. In this example, it actually annotated it for us. You can see in this example, it gave us adenylation domain of the non-ribosomal peptide synthase. All right. In this case, it tells us where it aligned. So we can go to C full alignment, resubmit. Okay, you can see this is where it aligned. So we can go to download, FASTA alignment, and we can paste this here. We can go to rename, and we'll call this amino acid domain search. Okay. Next, I'm going to go to JavaView, and I'm going to upload this alignment from file, and I'm going to change the file type .aln, amino acid domain search. Click this. I'm going to scroll. My top sequence right here is the sequence that I got the amino acid domain from. So here it is. This is it. So I'm going to take all the sequences that lined up with this one, or all the residues, go until it ends for the top residue, for the top sequence. Okay, so this is it. I'm going to selection, output the text box, FASTA. I'm going to go to new window, and I'm going to highlight the whole sequences. I'm going to go to edit, and I'm going to remove all gaps. Edit, remove empty columns, edit. Okay, that's good. So now notice we have one sequence that doesn't have anything matching with it. So we can click on it, selection, and then we're going to need to cut. So that's gone. So now we just have 5 sequences, the one that we started off with. and we have the, so these are sequences, and we took out, these are sequences that aligned with the amino acid adenylation domain. Okay, so we're going to select the whole thing, selection, output the text box, .fasta, and remove any gaps that are on here. So now we just have sequences, just have just the amino acid that are within the adenylation domain, right? And now we can take this sequence, and we're going to go to File, we're going to go to Save, and I'm just going to save this as amino acid domains .fasta. So these, supposedly, these are amino acid domains that are similar to the one that we initially extracted out from the grammacidin non-ribosomal peptide synthase. So we're going to save this, and you have to remove the gaps, and it just needs to be only the residues themselves. There's the sequences themselves, no gaps, nothing extra, or Mimi will not allow you to submit the job. So next, back. Then what we're going to go to do is we're going to go to Mimi. We're going to go to Mimi, and we're going to click on choose a file, and then we're going to do amino acid domains .fasta. Submit this. Okay. I'm going to keep everything default in this example, and I'm going to click search. So now we have our sequences, and we're going to be using these for Mimi to construct a de novo motif using the sequences we just submitted. Now I just want to go over what we just did one more time just for clarity. So all we did is our main goal was to construct a de novo motif using de novo motif of sequences that are similar to the adenylation domain that's found in grammacidin S synthase. So we went to the web page at Uniprot for the grammacidin S synthase. Then we went to the link to Interpro to find where the amino acid adenylation domain is located in the sequence itself. From there, we used the software JalView to upload it, or to extract the sequences the sequence that's responsible for the amino acid adenylation domain. So that's position 66 and 460. Now we only have just the domain in FASTA format. We're going to use that and search it against NCBI database. And we can do that. I used SmartBlast to do that for me. So I use SmartBlast, search the database, it chose some sequences for me. That's it. Yes, chose some sequences for me. And then all I did is I took the sequences that I lined up. Notice how in the SmartBlast I have circled here, and it shows me that this is my alignment right here. These sequences right here, this position in the sequences, the dark green, is what I lined up. I want to take out those sections. I just only want to take out in each sequence that section to use for Mimi Suite to create a de novo motif. And you see right here, this is what we're interested in. Only this, with what's in this box, is what I want. That's what I want right here. Nothing else. I just want to get those amino acids. So I'm going to use I'm going to use JalView for that. And as I showed earlier, I just found the alignment where they're lined up, and I extracted each one, and then I removed the gaps so Mimi will take the sequence. If you have the gaps in there, the Mimi will give you an error saying that the file is not readable or something like that. And then from there, once the results come back, I will show you the rest. Okay, so now, since we have our results from the Mimi search with the adenylation domain, click here, and here are our discovered motifs from Mimi. So we open up this, we have the E values, our P values again, which are really low, which is good, really low E values. And then we can still submit and do the same thing like we did with the first example using Mimi. We can do MAST and then do TomTom. But remember that Mimi creates motifs that have no gaps, so ungapped motifs. If we go back and click on GLAM2, GLAM2 discovers novel gapped motifs. Okay, now this example we're going to be also using GLAM2 for gapped local alignment motifs. Remember, Mimi discovers ungapped motifs, discovers novel ungapped motifs, and then GLAM2 is gapped motifs. And it's pretty straightforward. We do the same thing like we did in the Mimi search. We take our file with the adenylation domain sequences that we gathered, and then we can keep everything as default for now and click Start Search. After that, once we get our results back, I already had one running, and we can go to GLAM2, and these are be our output. So here are our sequences. Our motifs. So these are the discovered motifs using GLAM2. And then it gives us the marginal score. The greater the score, the better. And here's the start and end. Go down, we can look at each individual one. So here's the score, it gives us the scores for each one. Okay, in this example we're only going to look at the first one found. And we're going to scan alignment 1 against a sequence databases using GLAM2 scan. So we click scan alignment 1. What it's going to do is it's going to use GLAM2 scan. It's going to take our motif, the first one that we have right here, and search it against a database. In this case, we are going to do a fungal organism. So we scroll down, Candida glabrata, and we can click version 34, and then you can click Start Search. This will search for sequences that match with the motif that we have. So in this case, I already have one running. Okay, so after we submit our job to GLAM2 scan and we get our results back, we can click on GLAM2 scan HTML output. And here is our top result, 28.5. So this is the best score, it's positive. So next, what I'm going to do is I'm going to take this, the name of it, copy, then I'm going to go to NCBI, and you can just submit the name into the search box. Once you get your results, You can click on the protein sequence here. You can go to FASTA. From here you can take the actual protein sequence and copy and paste and submit it to a website called CATH. CATH. So CATH is used for analyzing protein sequences. So if you could click on Home and you go to Go, and then you click on, you have the search box here or the analysis box here. Put this in there. You're going to click Search. It's going to analyze the sequence. Once it's done, you'll see that you can look at the results. You can go to Matching Functional Families, and you see here amino acid adenylation domain. So here we have found the amino acid adenylation domain in a previously unnamed protein product. So this could be potentially a non-ribosomal peptide synthase, and we were able to do that by using the motif that Mimi helped find, or not Mimi, but Glam2Scan. And here it is. I have it in the tutorial 2, which I will be uploading for y'all. And then I use CATH to annotate it for the amino acid adenylation domain, and it does have a really low E value. And that's the end of this tutorial.